Welcome to lesson 1.6 in pre-calculus, the first clip. Today in class, you looked at a scavenger hunt involving function composition, where you had to do some function operations and maybe even some function composition like f of g or g of x, where we plugged the first one, or we plugged the second one into the first. The learning targets for this lesson are that you can perform operations with functions, which you did in the pre-calc summer packet. Those operations were addition, subtraction, multiplication, and division of two or more functions. That you can find composite functions and state the domain, which we did a little bit. And then in the next clip, we'll be looking at that you can decompose a single function into two functions. So the purposes of this video are to look at composite functions and state the domain. Composition of functions. The composition of a function f with function g is defined by f of g of x. It's not red fog. That operator is function composition, f of g, which means we're plugging g into f. The domain of f and g includes all of the x values of the domain of g. So the one that was plugged in, any restrictions on that domain will be restrictions on our final function that map to g of x values in the domain as shown. So here's some of our x's that are in the g of x, the domain, that will be a part of the final function's domain. What does this all mean? Well, we can follow some basic steps when we're finding the domain. Most of us know from Algebra 2 how to plug a function in and evaluate it in another function. But we need to be able to state the domain. So the first thing you're going to do is find the domain of the inside function or the input function. If there are any restrictions on this domain, they will be kept there forever. They will be part of the final answer. Even if they disappear in the end in our final function, they are still part of that final domain. Then we're going to construct the composite function and find the domain of this new function. Find the new domain. If there's any additional domain restrictions when we create the new function, they will be added to the domain restrictions of the function that was put into the other one, the original function. And if there's any overlap, then we'll take the intersection of the two domains. Let's take a look at some examples of this. Finding f of g of x, which means that we are plugging g into f of x. Therefore, any restrictions that exist on g of x will exist in f of x. So I'm putting in, I have f is the square root of, so I start with f is the square root of x minus 1. And we are putting g into that, x minus 1 squared. When I square x minus 1, I cannot just distribute because there's a sign in there. There are two terms. It's a binomial, so I have to expand it as x minus 1 times x minus 1. This function by itself, the x squared minus 1, has no domain restrictions. It's all real numbers. So I'm happy because I don't have any restrictions to worry about yet. So as I do this, I have x squared minus x, so that's minus 2x plus 1. Well, that's what I get after I square that, and I still have this square root and minus 1 that is around the function. So now when I combine like terms, I have x squared minus 2x, the square root of that. I cannot break this down because these are two terms. The most I could do would be to factor it as x by x minus 2, but I can't do anything more than that in terms of finding f of g of x. Either one of these two answers is acceptable for finding the composite function, because this is not a perfect square that I can factor out. Now, when I do this, I have to consider the domain restrictions. So I know that x by x minus 2, that radicand, or x squared minus 2x if you want, has to be greater than or equal to 0 because it's under a radical, with an even root. So the number in there must be 0 or positive. That's why the radicand has to be greater than or equal to 0 for these. Now, if you remember, we did one like this in class. This is the tricky one. If it were a linear function like x minus 2, it would be simple. X is greater than or equal to 2, we would be done. But when it is a polynomial function, we're not sure, right? Is it x is greater than or equal to 0, or x is greater than or equal to 2, or both, or a mix? We need to look at the number line to figure this out. So I have 0 and I have 2, and I'm going to plug in this function, the square root of x squared minus 2x. And I'm going to go to my table, and I'm going to plug in, we already know 0 and 2 will give us the 0 because they work. The question is, what happens to the left? To the left of 0, I'm getting actual outputs. So on my number line, I know that 0 works, so it's a colored in dot, and it goes this way. Between 0 and 2 is an error. So there is nothing between 0 and 2. And then from 2 on, I get values again. So it's going this way, and 2 is solid. So in interval notation, the domain for this new function, now remember there were no domain restrictions on g of x. If there were, we'd have to include them here. The domain for this function is negative infinity in interval notation, negative infinity up to and including 0, and 2 including 2 up to infinity, or toward infinity. It goes on infinitely. So there's our domain for f of g of x. Doesn't have anything from g of x because none were there. Let's take a look at this next function. We have f of x being this, g of x being this. So I have f of x, f of g of x is going to be 1 over x plus 1. I'm going to look at this and say, well, let's see, g of x right here was all real numbers, so I had no domain restrictions to begin with. Lucky me. If I were doing g of f of x, I might have some domain restrictions. So when I plug in x squared minus 9, I am going to have some restrictions now because it's in the denominator. There were no restrictions in the original g of x, so we're happy. And this one, though, this gives us 1 over, when I combine like terms, x squared minus 8. This is f of g of x. I cannot do anything else. By the way, it should have had that. Anything else with this function. So this is my function, 1 over x squared minus 8. Now, just like any other domain restrictions, I look at this and I say, well, x squared minus 8 equals 0. I'm finding the restrictions. If I add 8x squared equals 8, take the square root, x is plus or minus the square root of 8, which is plus or minus 2 square roots of 2. So what that means is x cannot equal that value, right? These are what x can equal. X squared minus 8 can't be 0 because the denominator would be 0. So in interval notation, the domain for this function is negative infinity up to negative 2 square roots of 2, and all numbers between negative 2 square roots of 2 and positive 2 square roots of 2, and all numbers from 2 square roots of 2 to infinity. If it helps you to draw a number line, let's look at where those roughly are. 2 square roots of 2 and negative 2 square roots of 2. We're looking at 2.8 and negative 2.8. We know that x can be any number to the left of this, any number to the right of it, but it cannot be either of those two values. So I have 1, 2, 3 intervals for my domain restrictions. So once again, we didn't have any domain restrictions on g of x, so yay, we didn't have to worry about that. But we did have domain restrictions on the final function, and so that's what these are right here. As we look to our last problem, we have some domain restrictions immediately. X minus 3 must be strictly greater than or equal, not strictly, it can be greater than or equal to 0, which means x has to be greater than or equal to 3 is something that will never go away. Must be included in our final answer for our domain. even if it disappears when we're done. So for this function, f of g of x, I have x squared was the f of x function minus 2. I'm plugging g of x in there for the x in this function. That's the square root of x minus 3. And we don't see any problem except, hey, look at this. When I square it, yay, the square root goes away. I now have x minus 3 minus 2, which is just x minus 5. F of g of x equals x minus 5. This is a linear function. And so you're like, hey, it's a line. There's no domain restrictions for a line, right? We're like, yay, all real numbers. But don't forget, you have to go back to the original g of x. It did have domain restrictions. So even though this is a linear function, the function we plugged into it had domain restrictions that will be a part of this function's domain restrictions. So we will have x is greater than or equal to 3, nothing to merge it with in this case. So it's just 3 to infinity. And you're looking going, why does that linear function have that restriction? Well, this function standing on its own doesn't, but because it is a composite built out of something that did have restrictions, we have to include those restrictions for its domain. This concludes the video clip. Oh, no, it doesn't. I'm sorry. We have 2 more functions to look at. I wish it included it. All right, so here we go on this one. This one doesn't have any domain restrictions. Neither does that one. Isn't that convenient? So we've got f of g of x. F of g of x. Let's take a look at that. In this case, you know what? I'm going to switch these just because I want it to have domain restrictions. It could get really ugly though. All right, let's do this. We'll just do it like this. This one has no, it's all real numbers. So we're like, yay, all real numbers, yay. All right, so plug this in, we've got 3 over x. For this one, we've got the square root of x plus 1. We're plugging g in. Plugging g in. When I'm done here, there were no domain restrictions here, but when I'm done here, I have now 3 over x squared minus 1. I can't do anything. I can factor this, but it doesn't go away, and there's no common factors in the numerator to cancel it with. There are domain restrictions here. X squared minus 1 cannot equal 0, which means x cannot equal 1 or negative 1. When I factor this, right, x minus 1 by x plus 1, x can't equal 1 or negative 1. And so my domain for this problem right here, there's the function, f of g of x. The domain will be negative infinity up to, but not including negative 1, everything between negative 1 and 1, but not including those values, and everything from 1, but not including 1, to infinity. In our last function, there's nothing to do, so I drop the parentheses. When I subtract, I just have the square root of x squared. And I'm looking going, oh, that's cool. So the square root of x squared is going to be x. I do have to be careful here because there was a square root here. So before I dropped it, before I dropped that square root, before I simplified, I have to consider those domain restrictions. X squared had to be greater than or equal to 0, which meant x had to be greater than or equal to 0 before I simplified. So even though I get this function at the end, that's a linear equation, y equals 1, f of x equals 1, or whatever, f of g of x equals 1x, it does have this restriction from when I built it. So this domain is from and including 0 to infinity. Now I know that's a little backwards because you're thinking, well, this didn't have any domain restrictions, and the final one doesn't, but when I plugged it in, because I had that radical, this expression, before I simplify it, has to be greater than or equal to 0 before I simplify it. Let me look back to see if I missed anything like that here. I don't think that I did. They all worked the way they were supposed to, so we should be good there. We'll have some more practice with this tomorrow after your success criterion, and hopefully you pass the success criteria, but we'll look carefully at some of these functions and make sure that you are solid on this before we move on. Have a great day. Tomorrow you'll be looking at decomposing a function after your exploration.